Good afternoon. My name is Thomas Tucker. I'm an engineer within my organization's IPNOC, and today we'll be configuring dynamic routing on the 7750 service router platform from Nokia, former alcatel-lucent. This module is also going to introduce bidirectional forwarding detection, routing policies, and debugging. And we're just going to assume that the reader is familiar with the router interfaces and the overall concept of link state protocols. That being the exchange of routing information between non-directly connected peers. All right, so we're going to have quite a few goals during this module, so this one might run a little bit long, but debugging wise, we're going to observe the ISIS adjacencies forming, and we're also going to take a look at our link state protocol data units, our hellos and whatnot. Our goals for routing policy is we want to allow direct or local routes to be redistributed into our IGP. And we're also going to apply this routing policy to our IGP as an export policy. And our goals for ISIS: configure the global router ID on each SR. The router ID will match the system address. So this is just going to be an easy way for all the protocols for this router to be identified within specific protocols. Configure all service routers or intermediate systems with an area ID of 49.00. All of them are also to be level 2 only, and configure each router interface participating in ISIS as a circuit of the point-to-point type. Also configure a wide metric of 5,000 on each router interface participating in ISIS. Configure MD5 authentication using the key MyISIS key, and enable IPv4 BFD within the ISIS protocol. And what that's going to do is that's going to give bidirectional forwarding detection complete control of those adjacencies. So instead of ISIS relying on its hold timer, which is, I believe, about 27 seconds, 27 or 30, depending on the vendor, we're going to allow BFD to control that adjacency. So we'll be able to tear down those adjacencies in less than a second, typically. And our goals for BFD, we're going to configure it on all router interfaces participating in ISIS. And we're going to configure it with a few parameters: the transmit interval of 100 milliseconds, a receive interval of 100 milliseconds, and a multiplier of 3. And we're not going to be able to do this in our virtual routers, unfortunately, but our last goal here was to alter BFD's default parameters to force the switch fabric module or control plane module to manage sessions. And that would have been done with the command type cpn-np, or control plane module network processor. So the first thing we're going to get into, let's go ahead and get these routers started, actually. All right, so while those are booting up, we'll go over debugging. So there are a few ways to do this. The way we're going to debug is we're going to create a file. After we create that file that's going to hold all of our debugging information, we're going to create an event handler, which is what we're going to reference in the show log command. And that event handler is going to display the contents of our log file. So if we wanted, we have the option of writing the output directly to the session, whether that be an SSH session telnet session, etc. Just a remote connection. We could also write that output to the console port if we have a console cable connected to our switch fabric module or control plane module A or B. But the way that we're choosing to do it this particular time is we're going to create a static file on our compact flash card, and we're going to store all the contents of our login information in that file on our compact flash. So running through the commands here, we have the command configure log file ID 66. So this is going to create our log file, which we're given the unique identifier 66 for our debugging information. And then once we're inside the context of our log file ID 66, we can give it a description. In this case, it'll be file for log ID 66. We'll specify the location, which is going to be compact flash 3. And we'll also give it 2 parameters, rollover 60, retention 24. And what that's going to instruct the router to do is automatically log the rollover, roll the log over every 60 minutes and retain this log in its current state for at least 24 hours. The only command that's required is the location. So once we have our log file created, we'll go ahead and create our event handler. And that's going to be using the command configure log ID 66. And under here, we can also give it a description, which will say log for protocol debugs. And our 2 essential commands on the event handler is from, where we specify where we want the debug information to come from, as well as to, where we specify where we want the debug information, or the logging information, I should say, to be sent to. In our case, we want the logging information from the debug trace commands, and we want that output or that data sent to the file with the ID of 66, which under our configuration, we know is going to be stored on our compact flash drive. And to view the contents of our event handler, we're going to use the command show log ID 66. So let's get back to N1. And again, we're going to be using the command window within Secure CRT. So we're just going to instruct it to send these commands to all the active sessions, or our 6 service routers. All right, so to configure our log, like we saw in our presentation, the first item we're going to have to do is our actual log file. So we're going to do that with the command configure log file ID 66. And pressing tab, we can see our options. The question mark, we'll get some definitions. And we'll add the description. The location is going to be compact flash in slot 3. And we're going to tell it to roll over every 60 minutes. With the retention of 24 hours. This is the configuration for our log file. And if we'd like, at this point, we could see if our file's been created. I'm assuming it has. With the command / file directory log. And it hasn't. Let's see if it's created once we save the configuration. No, so we probably have to create our event handler, and then once we reference the file in an event handler, SROS creates it, which makes sense. So let's go back into our log context. And again, we have our file ID created, which is going to host all of our debug output. So once we've got the file created, we can go ahead and create our event handler, which is what we're going to reference through the show log ID command. That's going to display the contents of our log file. So since we're already in the configure log context, we'll just specify log ID 66. And again, tab will show us our available options. Question mark gives us some definitions. And just for the sake of example, we'll go ahead and say our description, event handler for debug, output. And again, we want the output from. You can say we have a different source stream. So if we want a particular type of message, whether it be main, security, or change, in our case, debug trace, we can specify that here. And then 2, we can output this information to the console if there's a cable connected to our switch fabric module A or B, to memory, to our session, to an SNMP server, to a particular syslog ID. In our case, we're going to store all of this in our file, which is log file, file ID 66. And this is the configuration of our event handler. So if we go back to the configure log context, you can see the configuration of our log file, as well as the configuration of our event handler that's going to reference our log file. So let's go ahead and save that, /admin save. I'm also curious to see if the operating system's gone ahead and created our log file. So we'll say /file directory log. And yeah, so it went ahead and created it. So once the log file is referenced in a particular event handler, then the operating system goes ahead, it goes ahead and creates that log file in the log directory on our default compact flash in slot 3. So we can show the contents of our log file with the / show log ID 66. And of course, we haven't debugged anything, so it's empty, but as we can see, we've got our description. So Control-Z is going to put me back in the root context. And we'll go ahead and do the same for all of our other service routers. We'll configure logging on those as well, but to speed things up a bit, we'll go ahead and use our commands window. So just like we did on N1, first we're going to create our log file with the ID of 66. Then we're going to create our event handler with the log ID of 66. And we're going to specify that we want the output from our debug trace commands sent to file 66, which is what we created up here. All right, so configure log file ID 66. And the only mandatory attribute for our file is just the location. All right, so as long as we specify the location, that's all that we really need on our log file. So we'll go ahead and go straight to our event handler. So configure log ID 66. We're going to tell it we want the events from debug trace. And we want them sent to our file with the ID or the file ID, I should say, of 66. And we can say show log ID 66. And it's created on all of our other routers. So we'll just go ahead and save our configuration. But again, you can see how not going through contexts and just configuring these things, you know, in a flat way it saves a lot of time. Takes a lot of the guesswork out. So let's switch back to our PowerPoint. We've got our debugs created at this point. We're good to go on that. So let's move on to our routing policies. So what do routing policies, what's their purpose? Well, they allow routes to be controlled according to specifically defined criteria. And routes can be allowed or denied based on various parameters. That being the destination IP, the protocol, packet size, or the community list. Routing policies can also reference prefix lists. So if we want to only accept certain prefixes through some type of protocol or certain labels through LDP, we could, specify those prefixes or those labels in a prefix list and reference that prefix list in our routing policy. So in our module today, the goal of our routing policy is just going to be to redistribute directly connected or local routes into our IGP, which is going to be intermediate system to intermediate system. So here's the commands, the command set that we're going to use to create our routing policy. Not much goes into it. It's very straightforward. We use the command configure router policy options begin. And this puts the operating system in edit mode. So once it's in edit mode, we can go ahead and make changes to our routing policies. If you skip down to the bottom, you can see those changes won't be applied. Unlike the changes we've done thus far, these particular changes won't be applied until we issue this commit command. So first, we're going to enter the policy options edit mode. After that, we're going to define our policy statement or our actual routing policy, which in this case, it's going to be named export direct routes. And I just usually do this out of habit. It's probably a best practice, but specify the default action first. And after we specify the default action, we go ahead and create our first entry. And this is where things should look a bit familiar. Within our entry, we're going to specify where we want this information to come from. And in our case, we want it to come from the protocol direct. So these are going to be our local routes. Then we specify where we want the information to go to. In our case, it's going to be the protocol ISIS, which is going to be our IGP. And lastly, we simply need the action. So what do we want this routing policy to do when it matches this criteria? In that case, we want it to accept. And once we have our routing policy configured, we simply issue the commit command within the policy options context, and that'll apply our changes. So if we do this in action, just a quick rerun, we're going to enter the edit mode for policy options. We're going to define our policy statement, our default action, create our entry, then apply, or I should say commit the policy option changes we've made. So let's go ahead, get into the edit mode. We're going to do that with configure router. Policy options begin. Tab gives us our choices. Question mark, of course, gives us our definitions. All right, so now we're in the policy options context. This makes more sense now. All right, so what we're going to be concerned with is our policy statement. And I believe it was going to be called export direct routes. Again, the configuration so far for our routing policy, it is blank. And we're going to go ahead and specify our default action, which most of the time is going to be to reject whatever doesn't match the criteria. After we have our default action configured, we're going to go ahead and create our entry. And then we're going to specify the criteria is going to be from protocol. Just so you can see what you have available here. So we have area, AS path, path group, our level, prefix lists, tag, external. So there's all type of criteria that you can match from. In our particular case, we're going to be concerned with the protocol. And again, there's all the protocols. But what we're looking for is direct. The configuration for our entry. So once we specified from, we specified to, and that's going to be protocol ISIS. And last, we're going to configure our action, which is going to be to accept. And our action context, of course, has many different actions as well. You could actually tag routes. You can change the type, external type 1, external type 2, etc. Adjust the metric on a particular route, so there's no shortage of options. This is our entries configuration. We want data from protocol direct going to protocol ISIS, and we're going to accept. And our policy statement has our single entry along with our default action of reject. So once we're in the configure router policy options context, to apply these changes, we simply commit. All right, so we're going to do the same on our other routers. Again, we're going to do so in a flat fashion, and we're going to use the commands window to send our commands to all of the sessions. Control Z brings me back to the root context. And we'll look at our policy statement. All right, so we're going to specify configure router policy options begin. And of course, once we issue that command, we have instructed the service router to enter the edit mode for our service policy. So we can actually go ahead and create our policy statement. which we'll do with the command policy statement. And again, we were going to call it export direct routes. And we can even go as far as to specify our default action, which we want it to be reject. So once we've got our default action out the way, we can go ahead and specify our entries, or our entry, I should say. So for entry 1, we wanted it from protocol direct. And we wanted it to protocol ISIS. And the last bit of configuration for our entry was our action, and that action was to accept. All right, now we'll go ahead and commit our routing policy with / configure router, policy options, commit. And we'll go ahead and / admin save the changes on our routers. And for sanity check, we'll go to R6, enter our configure router context. And as we can see, we've got our routing policy. So our policies are configured on all of our routers at this point. The configuration is saved. Moving back to our PowerPoint. Now we're going to get into dynamic routing, and not too much into the theory. Just we're going to sort of lightly brush over things, might refresh things slightly, but this certainly isn't a module for like the theory of link state routing, the theory of intermediate system to intermediate system. But an IGP, or interior gateway protocol, is used to exchange routing information within a routing domain. Service providers typically use a link state IGP to achieve internal route redistribution within their routing domain. And learning routes dynamically will allow N1 to reach N6, even though they aren't directly connected. So in the end of our last video, even after we'd had established our physical connections and bound our physical ports to our logical router interfaces, the routers still could only ping their directly connected interface. Okay, they couldn't even ping an interface on the same router that wasn't directly connected to it. So our dynamic routing is going to solve that. It's going to allow N6 to gather all of its routes, its available routes, or its direct routes, bundle them up into a type length value, throw that inside of a link state protocol data unit, and send that over a adjacency to its neighbor. And once all the neighbors have the routes, of course, they begin building their tree using the shortest path first algorithm. And of course, the end goal of any link state protocol is for all of the members or speakers, or in our case, all of the intermediate systems, to have the exact same link state database. So they all know about the available links to any given host within their particular routing domain. So this is what our intermediate system to intermediate system topology is going to look like. We're going to have an area ID of 49.00, and it's going to be level 2 only. So the level capability for our intermediate systems is going to be level 2 only, and our links are going to be level 2 only as well. And also, as an overlying protocol, we're also going to be running bidirectional forwarding detection over our ISIS adjacency links. And we'll get into more of that in a bit. Let's see, I'm wondering if I should go ahead and get this topology out the way. Yeah, let's go ahead and configure ISIS. Why not? So getting back to our goals, our first goal is to configure the global router ID on each service router. And this is so that each protocol, this is so that the router will be uniquely identified automatically from now on. Every time we activate a protocol, this is what the router is going to be known as. In certain protocols, the default router ID will be the directly connected interface, which could make it difficult to troubleshoot. But in our case, we're going to force all of our protocols to use the router ID of whatever our system address is. So that's going to be configured within the configure router context. I guess I could back up. Configure router ID. And in the case of N1, our router ID is going to be 1.1.1.1. For N2, configure router ID. It's going to be 2.2.2.2. And we're going to repeat that for all of our routers. And 3 is going to be 3.3.3.3, and 4, all 4s, and 5, all 5s, and 6, all 6s. And we're going to go ahead and admin save on everything. So going back to N1, let's take a look at our router context. And you can see we've got our router ID configured. All right, so once we've got our router ID configured, then of course our next step is going to be to go ahead and configure our IGP, which is in our case is going to be ISIS. And we're going to make everything a part of area 49, or technically 49.00. So once we enter the ISIS context, I'm not going to go through all the options, but pressing tab, you can see what you have available. Right now, we're concerned with the area ID. And again, we're just going to make that 49.00. And we're going to rinse and repeat that on our other routers using the command session, or actually the command window, I should say. So we're going to say / so that the router understands our command regardless of the context that we're in. Configure router, ISIS, area ID, 49.00. Thus far, this is our configuration that we have for ISIS. We've specified our area ID. All right, next, configure all service routers or intermediate systems to be level 2 only. That's going to be done through our level capability context. So we're going to specify our level capability is going to be level 2. For these other routers, we'll just Just have them sort of ride along with us here. All right, so as you can see, so far we have our level capability and our area ID configured under our ISIS configuration. So next, configure each router interface participating in ISIS as a circuit of the point-to-point type. Now, before we do that, I'm going to go ahead and configure our system interfaces as passive. Okay, and that's just going to be done with the configure router ISIS interface system passive. And just for the sake of congruity, we're also going to make our system interface level 2 only. All right, so what we've done is from here, should have done it here. We've gone into the interface system context and we've specified the level capability of level 2. And we've also specified passive. So if we look at our configuration for this interface, this is what it would look like. And that's all we need for our system address, or our system interface, I should say. So now we're going to go ahead and configure the interface facing into. Go back to our topology. This interface is participating in ISIS as well as this router system address. So now we're going to go ahead and configure our interface on into. Well, on N1 that's facing into. All right, interface to N2. And with this, we're also going to specify our level 2 capability. But here we're also going to specify our metric of 5,000, which is one of our requirements, as well as configuring it as a point-to-point circuit type. So here's our core facing, the ISIS configuration on our core facing interface. It's going to be level 2 only, point-to-point, and our metric is going to be 5,000. So if we go back, let's just take a look at our ISIS configuration so far. We've got our system interface as passive. We've got our network or our core facing network interface up and advertising. So now we, before we do the authentication, I want to bring this adjacency up. Let's go ahead and add and save that, just so that we could take a look at, put our debug to use. So what we're going to do is we're going to bring up the adjacency between N1 and N2. And after this adjacency is brought up, I'll configure authentication on N1 and take a look at our debug file to see what it tells us. Whether or not, of course, this adjacency can't stay up, but we're just going to have a look at our debug so that we can see the type of information that we might see coming across our adjacency. All right, so from N2, we're going to do the same as we did for N1. Let's take a look at our ISIS configuration on N2. All right, so we've got our level capability configured, our area ID configured, and one thing I have not seen yet is we have to specify that we want wide metrics only for our ISIS configuration. So we'll specify that with the command /configure router ISIS wide metrics only. I didn't think that was it. Let's see, what's the correct command? I believe it's level 2 wide metrics only. Okay, yeah, that was it. So if we did it jumping through context, once we're in our base ISIS context, we would specify level 2, and this is where we configure our wide metrics. All right, much better. Let's go ahead and admin save that. Got 25 minutes, good. All right, so back on N2, let's take a look at our ISIS configuration. So all we're gonna do now is let's do a show router interface. And we see we've got 2 interfaces that we want to bring up ISIS on. So we'll go ahead and do that. Again, we've got our system interface configured as passive with the capability of level 2, so that's perfect. So on N2, we'll specify the interface to N1, the level capability. It's going to be level 2. Our level 2 metric is going to be 5,000. Our interface type is going to be point-to-point. And if we do a stare and compare, we're good to go. So our adjacency rather should be up. So we'll check it out with show router ISIS adjacency. And sure enough, as you can see, our adjacency is in an up state. And now that we have our adjacency, we should be able to receive some ISIS routes. Show router ISIS routes. And as you can see, we are receiving N2's system address through ISIS. So we can also look at this in our route table, show router route table, protocol ISIS. And if we wanted to look at it in our fib, show router fib 1 all. All right, so now that we have an adjacency up, we know ISIS is capable of working between these 2 routers. Let's go ahead and break it just a bit so we could see what our log shows us. So on N1, we're going to go back into ISIS, configure router ISIS, and we're going to shut it down. And once it's in the shutdown state, we don't need to shut it down to do this, but I wanted to shut it down just so it wouldn't start generating debug information. But we're going to use the command tree flat. and match on debug so that we can see all of the available debug options that we have. And as you can see, Nokia does not disappoint. All right, we're going to be concerned with debugging our ISIS adjacency packets. So we're just going to specify debug router, ISIS adjacency, and our interface to N2. All right, so we could do show debug, and that'll allow us to see exactly what we're debugging on. Our adjacency using the logical router interface to N2 within the ISIS context. All right. And just for the sake of doing it, we'll show our log ID 66. You can see it's empty because ISIS is still in a shutdown state. And before we do that, let's see, what were our goals? We've got authentication and BFD. Let's go ahead and apply our export policy as well. So let's go into configure, router, ISIS. And we specify export. And by pressing the tab key, not only will SROS give us the available options, like we've been seeing numerous times in our output, but it also gives us what's configured. So if we have policies configured that are on the router and they aren't quite matching because of a case mismatch or something like that, chances are we'll still be able to identify the correct policy. So this is one of those features that you want to know that you have at your disposal. So even if you don't remember the name of an ingress filter or an egress filter, pushing the tab key will allow you to see what options are available on the particular router. In our case, we're going to use the export policy. Oh wow, up to 5 policies. So just in case you're curious, you can apply up to 5 export policies on the intermediate system to intermediate system. So we're going to specify our export policy of export direct routes. And we're going to do that on N2 as well. And to be honest, we might as well just do it on all of our routers. All right, so let's take a look at our ISIS configuration. Again, it's still shut down on N1, but we're running a level 2 only intermediate system in area 49.00. We've applied the export policy export direct routes, which we'll get to in 1 second. We specified for level 2, we want wide metrics only. We've configured our logical router interface system to be level 2 only, as well as passive. And we've configured our logical router interface to N2 to be level 2 only as a point-to-point interface or circuit, and also with a level 2 metric of 5,000. And again, on N1, we are debugging our ISIS adjacency packets through our logical router interface to N2. But getting back to the export direct routes, if we go back and we go into our policy options context, we can sort of walk through what this routing policy is going to do. So if none of the criteria match, we know that it's going to reject. So when we take a look at our criteria that we've specified in entry 1, we want the directly connected routes. So we want to take the prefixes from the directly connected routes and send them to ISIS. And whenever that criteria matches, we want those prefixes to be accepted. So our intermediate systems are going to export their directly connected routes into ISIS. So let's go to N6 for a second. Let's see. Let's take a look at it in our route table or our fib will have what we're looking for. So let's do it in both. Show router route table to look at the routing information base. Show router fib1 all to look at the forwarding information base. But what we're concerned with is local. Now, in our routing policy, we specify protocol direct, but this is probably just one of those, things that got overlooked. But our protocol, as we can see in our fib and even in our rib, is going to be local. There's no difference between the protocol local and the protocol direct. The only slight difference or cosmetic difference is that direct is what we refer to it as within our policy options. However, local is what it's referred to as within our control plane. Or our routing information base, I should say, sorry. And our forwarding information base. But they're both the same thing. So we're instructing through our routing policy that we've applied as an export policy to ISIS, we're instructing ISIS to take these prefixes, our system address of 6.6.6.6/32, and our directly connected address of 10.5.6.6/32, and export those prefixes into ISIS. Now, the thing is, ISIS already does this by default. Anytime you enable ISIS and an adjacency forms, the directly connected interfaces are going to be exchanged in type length values within those link state updates. That's just what the protocol does. The only thing that it doesn't do by default is exchange the system address. But we could have done that with a redistribute connected command, or redistribute. Let's see, what would it be called on SROS? Tree flat. Let's see. So I don't think SROS has a redistribute connected. Command like ISIS does. But the point being, when we put the system address into ISIS as a passive interface, it's going to redistribute that address. It just won't form an adjacency over that address because we've specified we want that interface to be passive. So it's going to put that address in ISIS. It just isn't going to form an ISIS adjacency over, using that address. So let's get back to our routing policy. So again, we're just instructing the router to take our directly connected prefixes or our local prefixes and export them into ISIS, which ISIS already does by default. So we aren't doing any magic here. The only thing we're doing is introducing ourselves to routing policies, sort of dissecting those policies, seeing its moving parts, what has to be there, what doesn't have to be there, and applying that given policy to our particular protocol. All right. So we've got our routing policies configured on everything. Control Z brings me back to the root context. Let's see how much time I've got. 10 minutes. No, I don't want to run through authentication in 10 minutes. Well, let's try it. So our next goal is going to be to configure authentication. MD5 in particular, and we're going to use the key authentication, the key my ISIS key. And you know what, let me just go ahead and restart these routers because 10 minutes just isn't going to be enough time. Go ahead and save everything. Sure we saved. We'll reload. And while these boot up, let's see. So what we're going to be doing is we're going to be configuring all of our intermediate systems to use MD5 authentication, just so that, you know, we aren't compromised in some type of man-in-the-middle attack. A router can't pretend to be part of our intermediate system within our routing domain if it isn't really belonging there. So this is a standard thing you'll see, hopefully, in a service provider environment. It's just MD5 authentication across links that carry peering traffic. And once we've got our authentication taken care of, we'll get into our bi-directional forwarding detection. This is another one of those amazing little protocols. So they're coming around. All right, so we're just going to log in here and going right back to where we were. Configure router ISIS. Again, ISIS on N1 is still shut down. We might have to re-enable our debugs. Yeah, so we'll re-enable our debugs by specifying the command / debug router ISIS adjacency and our logical router interface. All right, so let's take a look at our, of course it isn't up, it's shut down. But let's go ahead and re-enable ISIS. And what this does is it starts the ISIS daemon up, and the ISIS daemon sees this interface, generates the correct ISIS hello packet based on our configuration, and forwards it out this interface. So let's take a look at our adjacency. And our adjacency is up. So let's take a look at our event handler. Show log ID 66. And we can see we've captured our adjacency. Went from initializing to our three-way state. Or our init. And it acknowledged our three-way action. And we could see our level 2 adjacency with router N2. We could tell by our router ID 2.2.2.2 is up. And just to test, we can ping router 2 system address. And even from router 2, we could take a look at our fib, and we should see, so router fib 1 all. Our ISIS route for N1. All right, so now let's take a look at authentication. Again, we aren't going to spend too much time on this. We're going to specify the authentication type. See the options we have available. And of course, message digest being MD5. And we're going to specify our authentication key. my-ISIS-key. If you take a look at the configuration, we can see that our authentication type of MD5 is there, and our key has been hashed. All right, so let's take a look at our adjacency. And we can see our adjacency no longer exists. So if we look at our log, you can see that we've definitely lost our adjacency with N2. All right, so now what we could do is we could debug we could debug the actual ISIS packets. So sort of go inside of them and see if that offers us a little bit more information about why our adjacency was lost. So we're going to use the command tree flat, match on router ISIS. And let's select the packets. So we're going to do debug router ISIS packet, and we're going to do a point-to-point hello. Since our circuit type is point-to-point, and we'll specify our interface, which is 2N2. And we don't have to do the detail, but we'll just do the detail just because it's there. So I'm going to shut down ISIS with / configure router ISIS shutdown. And then I'm going to clear the contents of our log. And then I'm going to bring ISIS back up. And see what's in our event handler. All right. So taking a look at our ISIS PDUs, You see our PDU type. It is an IIH, or an ISIS hello packet. We've got our length, our source, our router ID, our interface address. So this is where our type length values are going to start coming in. Our three-way adjacency, our state is down. We also have our authentication TLVs, specifying MD5 with our particular ISIS key. And if we move on to a packet that we've received, we can see that our source ID for this one is router N2, or 2.2.2.2. And this is again an ISIS hello protocol data unit. And we've got our TLVs right here. Notice there's no authentication TLV. So let's quit right there. So let's move up to what we're transferring. So this is a hello PDU that we're transferring. Our TLVs, as you can see, again, our authentication. And this is a hello PDU that we're receiving, stuck in an init state with no authentication TLVs. So let's just turn off debugging. Because I like to show you, just instead of going inside the packet with detail this time, we'll just debug the messages, because it should tell us no authentication configured, or authentication mismatch, or something similar to that. So let's do debug router ISIS packet point-to-point hello, router face 2 into. Let's clear our log. Okay, this is what we wanted. So without the detail, with the detail, we were able to go into the PDUs themselves and witness that the PDUs we were receiving didn't have the authentication TLVs that the PDUs we're transferring did. But without specifying the detail, ISIS sort of tells us. And acceptance check failed for the PDU received. It was a point-to-point hello. And why it failed? It was an authentication failure, null TLV. So it's telling us, so actually this is a good thing. So null TLV, so it's telling us that that type length value for authentication doesn't even exist on N2, which is a good thing. So we could go into N2 and let's go configure router ISIS. Let's see, okay, let's take a look at the ISIS config. And you know what, I agree. We don't have that particular type length value for authentication. All right, and let's see. So we'll go ahead and do that. Authentication type, again, it's going to be message. Now let's give it the correct TLV, but let's give it the incorrect. Authentication info. Let's see what our log looks like then. All right, so again, previously we were receiving this error message. Our intermediate system couldn't accept this hello PDU. because there was no authentication TLV included. So now it's telling us that the error is no longer that it's a null TLV. The authentication is simply failing. So it's reading the type length value, and the authentication within that type length value doesn't match what we have configured on router N1. And just for the sake of closing the loop, let's take a look at the ISIS hello in a little bit more detail. In particular, one that we're receiving. So here goes one. So here's one that we're receiving, RX. And again, this is originating from the intermediate system with the router ID 2.2.2.2. Here are our TLVs. So we've got one for our area address. We've got one for our supported protocols, the interface. And here's our ISIS key, which of course is incorrect. Just out of curiosity, I just want to see, compare the hashes here. Okay, I didn't, I was hoping it wouldn't do that. So that's a good thing. But anyway, so this adjacency still isn't up. Show router ISIS adjacency. N1, let's see if we get something on N2. No, but I mean, we're looking at the log, so let's just show log ID 66. So we added the detail. All right, so it's telling us why the adjacency is down. Authentication failure. So we know that we've entered the wrong authentication key on N2. So this is the key we entered. So once we enter the correct key, which is my ISIS hyphen key, we'll see our adjacency come up. Okay, so we didn't see it because we're debugging the point-to-point hellos. So let's do debug router ISIS adjacency. And we're just going to bounce ISIS. Just to get that adjacency to restart. We can have some good data in our event handler. So show log ID 66, which is our event handler. And we can see our adjacency is now up from init to three-way to up. All right, and just for the sake of checking it out, we'll look at the link state database on N1. So show router ISIS database level 2, and let's see, what would N2 system ID be? Here we go. Detail. And here we can actually look at our TLVs that we're receiving from router into. So we've got our TLV for our area address, our host name, our interface address, our traffic engineering, should we configure it, but most importantly, our authentication. And you know what, we could actually, let's check that out at the packet level. Just so we could see it live in motion. All right, C-snaps, complete sequence number, protocol data units. These are routing table updates. We won't get into those. What we're concerned with are our hellos. Well, we'll look inside of it. There's no reason. I mean, there's no secrets in here. So let's look at. Let's dissect this a bit, just so we can see what's inside of it. So in our C-snap, we also have an authentication TLV, type 10, length 17. Ending B3. Now that looks familiar. Let's see. Debug router, ISIS. Packet, point to point hello. To detail. Yeah, I just want to see, I just want to compare these hashes. Let's see, ending F3. Nope. Nope. But anyway, this is inside of our C-snap. Let's take a look inside of our hello. Okay, this is what I was looking for. So inside of our hello, we've got our type length values, and let's just, so that we can see what this looks like from the router's perspective. We're going to look at N2's instance in our link state database. Again, several TLVs. But let's just, I mean, let's just look at it from the debug and the Wireshark, just to say we did it. All right, let's see. So a PDU that was received, this is one we're looking at here. Let's just scroll down to the TLVs. That's what all we're going to be interested in. So these right here. So our area address TLV, we could see that it's a type 1 length 3, and it does contain our area 49.00. Our protocol supported TLV, type 129 length 1, and that's the network layer protocol identifier, I believe. And that's IP. or IPv4. Our IP addresses, this is our interface. Its type is 132, its length is 4, and it's 10.1.2.2, which is the interface on N2 that's facing N1. Our point-to-point adjacency state, type 240, length 15. The adjacency state is up, and it's got our neighbor system ID of 1.1.1.1. And last but not least, our authentication TLV. It is a type 10 length 17, and it contains our ISIS key, my ISIS key that's hashed. And we don't have to compare the whole thing, but we could see it begins with 7070 and ends with 2079. So just comparing, beginning with 7070 and ending with 2079. It's an add and save. So that's so you can see that SROS really does a very, very good job of decoding these packets, and you can sort of debug in peace now, or you could be a little bit more comfortable with debugging, especially because you can specify a file that captures all of this data. So it's not like with the Cisco, for example, you have to, you might have to open up an extra terminal with no debug all ready to go just in case you have to push the red button, because you never really know what what type of output you're going to get. It's I will neither confirm nor deny, but from what I understand, it's very easy to crash a Cisco device by hogging its CPU down, issuing debug commands without, the ability to disable those debug commands. So once you issue it, I mean, the CPU spiked to 100, so it's going to be impossible to issue the no debug. But a great way to issue the no debug is for the router to restart itself. That always seems to work. But getting back to our presentation, so we've got our MD5 authentication using the key my ISIS key. And what I'll do is I'll just go ahead and configure that on all of our routers. So configure or / configure router ISIS. Authentication type is going to be message digest. And again, our authentication key is my ISIS key. And /add and save. Now what we'll do is we'll go ahead and bring up our adjacencies. Let's see, on the other routers, sort of quick, fast, and in a hurry, but we'll slow down when it comes to bidirectional forwarding detection. So on N1, let's see, we're probably good to go on N1. Yeah, we've got our interfaces in there. Let's check N2. All right, so we've got to add our interface that connects N2 to N3. So we're just going to say interface to N3. All right, that's what we want. So we're just going to blow through this kind of quickly. All right, now let's check our adjacencies. We do have an adjacency to N5, so we'll know this is working because we'll have a ISIS route for N1's system address in our forwarding information base. And we do. So let's just take a look at all of our ISIS routes, show router route table, protocol ISIS. So see, not only do we have all of the system or the passive interfaces, but we also have all of our directly connected interfaces as well. So this is the network between N1 and N2. This is the network between N2 and N3. Let's start that over. So this is the network between N1 and N2, /28. This is the network between N2 and N3, /28. This is the network between N3 and N4, /28. And this is the network between N4 and N5, /28. Of course, N5 is directly connected to N6, so that's going to be a local or a directly connected route. All right, so not only are our adjacencies working, but our export policy is working as well. So we're successfully exporting our routes from the local directly connected protocol into ISIS. But again, nothing that ISIS doesn't already do by default. Let's see, we have this full screen. Yep. All right, so that takes care of our dynamic routing. So now what we've got is our bidirectional forwarding detection. We'll get into that, and this won't take too much longer. But BFD, of course, stands for bidirectional forwarding detection. It is an asynchronous protocol, so parameters don't have to match up on each side for a session to be established. But it does have more than one mode. It also has demand mode, but you can read more of that. I believe the RFC is 5880. But what bidirectional forwarding detection does is it establishes a lightweight session between systems to detect link failure at an extremely, very quickly, pretty much. BFD messages are processed by the IONs by default, but if we go back to our goals here, one of our goals was to alter BFD's parameters to force the switch fabric module to manage sessions. Now, this isn't a capability of the virtual routers, but we would do that with the command type cpm np. And the reason we want to do that is to maintain that segregation between our forwarding plane or our data plane and our control plane. So we don't want the hardware that's responsible for forwarding data to also have to process control messages for bidirectional forwarding detection, because these messages come in extremely frequently, like maybe 3 or 4 milliseconds, or maybe like every 5, perhaps milliseconds, 5 or 6 milliseconds. BFD is sending a message and expecting an acknowledgement. So let's take a look at a situation that happens if we don't have bidirectional forwarding detection enabled. We've got 2 given intermediate systems that have formed an adjacency over a link that runs between these two 7450s. So N1 and N6 are our 7750 service routers, and switch 1 and switch 2, or SW1 and SW2, are our 7450 ES chassis. So let's assume that we have an adjacency between N1 and N6 that's formed and working just fine, and assume there's a link failure somewhere beyond either of the service routers' directly connected links. So in our case, this link failure occurs in between the switches. Now, in a real service provider environment, sometimes intermediate systems are directly connected, as in they're in the same colo, sometimes the same rack. Other times, if we're dealing with something like a backhaul circuit, these 2 routers are logically directly connected, but physically they might go through hundreds of miles of fiber, hundreds of, I don't know if hundreds, but quite a few pieces of transport gear, quite a few switches. It's multiplexed, it's demultiplexed. So there's a lot of potential opportunities for failure to occur, okay, if those routers aren't directly connected. So in our case, we have 2 switches that are separating our 2 service routers that have an ISIS adjacency built between them. Now let's assume that a link failure occurs somewhere beyond the directly connected link. So in our case, it happens between the 2 switches. From the service router's perspective, the link state has not changed. And this is because its connection to the switch is still up and functioning. That connection didn't go operationally down. Therefore, ISIS doesn't know that the adjacency is operationally down at this point. Instead, ISIS has to rely on the hold timer. And I believe by default, it's 27 seconds. So no link state changes are detected for at least 27 seconds, looking at the connection between N1 and switch 1. N1 believes the adjacency is up and forwards traffic into a black hole until the hold down timer expires, or the hold time expires. Likewise, looking at the connection between N6 and switch 2, no link state changes are detected for at least 27 seconds. N6 believes the adjacency is up and forwards traffic into a black hole until the hold down timer expires. Now, once the hold down timer expires, the protocol itself, ISIS, does tear down the adjacency. And once that adjacency is torn down, it recalculates the shortest path to wherever it's destined, updates its link state database, then floods that update to its adjacent neighbors. But again, that process takes 27 seconds. So suppose that this connection between N1 and N6, suppose it was some type of 400 gig lag from New York to Los Angeles. Well, forwarding 400 gigs per second, or gigabits per second, for 27 seconds, that's a lot of traffic that's being black holed. So for those 27 seconds until that whole timer expires, both routers are going to think that the adjacency's up because they haven't detected a link state change or a link state update because the state of their links haven't changed. Their connections to each switch are still operationally up. So let's take a look at what happens when we enter or when we configure BFD. So same scenario, we have a provider edge router N1 in Los Angeles and a provider edge router N6 in New York, and they're both running the same ISIS protocol, or the same IGP, I should say. But this time they've overlaid their IGP with bidirectional forwarding detection. So they've taken control of at the adjacencies from intermediate system to intermediate system and given it to bidirectional forwarding detection. So what does this mean? Well, let's assume the same link failure occurs. Because ISIS is no longer depending on link state updates, or no longer depending on that whole timer to expire, BFD is able to tear that adjacency down as soon as it doesn't receive or send a certain number of control messages. And it sends these control messages at such a high frequency that the detection time for bidirectional forwarding detection is extremely low, sub-second. Some devices can be tuned to be sub 50 millisecond detection time. So all BFD does is it sends UDP packets or control messages using UDP at a very high interval to a neighbor, and it expects those same control messages to be received at a very high interval originating from that neighbor. So the data within a BFD control message might be something, for example, just an integer that increments. So the BFD protocol on N1 increments the data field in this control message by 1. So the data field is now 1. It sends that control message to N6. N6 sees that control message and sends it back to N1. N1 processes the control message, sees the number of 1, understands that it set that data, and increments it to 2, almost like a loop. So as long as N1 sees the control message that it sent to its neighbor, it won't tear that adjacency down. And as long as the adjacency is up, N1 is going to continue to increment the data within that field. So that's how BFD is able to detect these failures so quickly, is because it sends and expects control messages extremely quickly as well. So if we move back to our service routers, $20, that's more than enough time. What we'll do is we'll configure BFD. And just referencing our goals, we're going to understand that we configure BFD on our logical router interfaces, but we enable it within our protocol. Hold on one second. All right, I'm sorry about that. I'm back. Let's see, where did we leave off? I believe we left off at BFD. Yep, so okay, so we're going to configure all of our router interfaces participating in ISIS, configure BFD on all those, with a transmit interval of 100, a receive interval of 100, and a multiplier of 3. So like we stated earlier, BFD is configured on the router interface itself and enabled within the protocol. But in case we couldn't quite remember exactly where within the logical router interface configuration we configure BFD, we can always use the command tree flat and match BFD. So we see that it's going to be configure router interface BFD to configure BFD on our logical router interfaces, and then configure router ISIS interface BFD enable to configure it on our, or to overlay it on top of ISIS. So let's go into our logical router interface configuration, show router interfaces, configure router interface, 2 and 2. BFD, let's take a look at our choices. So the transmit intervals first. Can we do 10? Oh, okay. So we can't go that aggressive. So our transmit interval is going to be 100. Then our receive interval is going to be 100. And then our multiplier is going to be 3. And this will satisfy our requirements for BFD. Transmit interval of 100, receive interval of 100, and a multiplier of 3. And under our interface 2 and 2, you can see we have our BFD configuration, and we can issue the command / show router BFD interface. You can see it is configured on interface N2. Let's do show router BFD session. And thus far we have no sessions as expected. All right. So what we're going to do is we're going to go ahead and configure BFD on all of our router interfaces. I'm going to run through this rather quickly. So on N2, configure router interface. 2 and 1, the same BFD parameters. On router N3, configure router interface 2 and 2 with those same BFD parameters, as well as our router interface to N4. And we're going to rinse and repeat. All right, I'm going to issue our / admin save. Make sure that our configuration is saved. Let's also do / show router BFD interface, just to make sure that we've got BFD configured on our logical router interfaces. Excellent. And we could show the sessions. And as expected, No sessions thus far. Let's see, we still got Wireshark running. Let's keep Wireshark open so we can look at this on a packet level. But just to, I guess, refresh, earlier we took a look at our hello PDUs and all of our type length values, and we saw that SROS does an excellent job, does an excellent job of decoding our PDUs to make operating the network just that much easier. Every little bit helps. So now what we'll do is once we enable BFD, and you know what, before we do that, okay, so these routers are going to reboot here pretty soon. So I'm just going to save the configurations and reboot them manually again. And we will just start a new Wireshark session. All right, let's just take a look at our boot sequence here. And when these routers do get done booting, since we've got BFD configured on all our interfaces, we're going to go ahead and enable IPv4 BFD in ISIS, just so we could see the frequency at which BFD transmits and receives its control messages. So we'll debug those here within Wireshark. And I am debugging the connection from N1 to N2 in Wireshark, or I should say sniffing that connection. All right, now that we're back, let's go ahead and log in and let's show our show router ISIS adjacencies. Excellent. And I'm not sure if I completed this thought previously, but the test of our dynamic routing would be for N1 to be able to reach N6 sourcing its own system address, because N1 and N6, let's go back to our topology, N1 and N6 aren't directly connected. So for us to ensure that our dynamic routing is working properly, we have to source traffic using N1 system address, and we need that traffic to be able to reach N6. And likewise, traffic sourced from N6 with its own system address needs to be able to reach N1, which we'll do now. So from N1, we're going to ping N6's system address, and our source is going to be our own system address. We could look at this in Wireshark. Let's try restarting Wireshark. All right, that looks better. All right. So our uh, pings from N1 were reaching N6, and N6 responded to those pings, sourcing its system address with that traffic destined for N1. And just because we're here, let's take a look inside of an ICMP packet or Internet Control Message Protocol. As you can see under our IP header, we do have our source uh, N1 system address, our destination N6's system address. And within our ICMP message, we have a type 8, which is our echo request. And let's see a reply. So in our reply from router N6, we can see that we have a ICMP type 0. Which is our reply to the request from N1. All right. Let's see, let's just send a few more pings. Well, let's do a trace route. All right, so here's what our trace route looks like. And of course, trace route uses UDP. TTL5. TTL5. Yeah. So anyway, I'm getting distracted. So yeah, point being, we're sniffing across this wire and we're seeing the traffic go back and forth. So let's take a look at BFD. That's what we were headed toward. All right, so there's our ISIS network. And currently we have BFD configured on all of our logical router interfaces. However, BFD is not yet configured as an overlay protocol within our ISIS configuration. So we'll do that on N1 first. We'll say configure, router, ISIS. Interface 2 and 2. And we have our option BFD enable, IPv4. Let's see, include BFD type length value. I'm not exactly sure what that is. Include BFD TLV. I have no idea what that is. Let's see. But now I'm interested. It's fast. Took too long to respond. Is my internet not working? Let's see. It's working. Is it a Google thing? Let's see. Hmm. Let's see. Maybe it's something with the VPN. Just for now, we're going to configure that include BFD TLV. I'm going to admin save. I'm going to see. Maybe it's this proxy thing. How do you find that crap in Windows 10? Is it internet options? Hmm. This is wild. All of a sudden, I have no internet. All right, so what I'm going to do is I'm going to reconnect to the VPN. And before I do that, I'm going to go ahead and stop all these, as it's going to drop me anyway. Okay, now let's see if once I disconnect from the VPN. Okay, so it's the VPN's fault. So we have an RFC here, which is cool. Yeah, let's open tabs on a couple of these RFCs. And then let's connect back to the VPN so we can get our routers back. All right, so now that we're back on VPN, let's see if we can connect back to our server. Let's restart GNS. And we're going to restart Wireshark as well. Okay, there we go. All right, so now we're back to where we were. So let's start all of our routers. And that should calm Secure CRT down a little bit. All right, so our routers are booting. And we left off with this weird include BFD TLV. So this is the RFC for it. It's RFC 6213. Let's see what this thing does here. Okay, so it's a particular TLV that specifies, that lets ISIS routers know that this particular intermediate system is running BFD. That's what it seems like. Okay, we know that. Okay, here you go, the problem. Hmm. This is very true. Uses CLNS. Okay, so the solution. Nice. Okay, so gotcha. So yeah, so this is a TLV that says I have BFD enabled. No, I forgot my VPN's all crappy. So I can't look at the network layer protocol ID, but we got the TLV itself. So it's a type 148, length anywhere between 3 and 255. 3 octets specifying the multi-topology ID or network layer protocol identifier for each topology or data protocol for which BFD support is enabled. Huh. All right, so this is a TLV that's new to me. Type 148, length 3. And it is the BFD enabled TLV. It allows a router to tell its neighbors that it is in fact running BFD. Oh, sorry about that. I'm back. All right, so yeah, so this is something that's new to me. I want to see this thing in action though. So all right, so we're gonna go ahead and log back into all of our routers again. Configure router ISIS on N1. Let's take a look at that configuration. And sure enough, on our interface 2 and 2, we've got BFD enabled for IPv4, and we're instructing ISIS to include this type 148 length 3 TLV. Or this is what this guy looks like. So include BFD TLV instructs ISIS to include type 148 length 3 as a TLV in its hello PDUs. So I'm just curious to see this thing in action. So I'm going to go ahead and configure it on all of our router interfaces in ISIS. Let's do the show router ISIS interface. Configure router ISIS interface 2N1. Oops. All right, so we've got that TLV, that type 148 TLV, enabled in our routing domain. I'm just going to bounce ISIS on everything to make sure that those hellos we have fresh adjacency. So / configure router ISIS shut down, and then / configure router ISIS no shutdown. We'll admin save that. How would we look at this? Let's do the ISIS database. Show router ISIS database /2. And by the way, now we have, although we only have a direct adjacency to into, our link state database is going to be the same on each router. So N1 knows the exact same thing as all the other routers, knows the exact same prefixes as all the other routers. So I would be expecting us to have this TLV in our database, and I guess I would be expecting us to be sending this TLV also. Let's take a look at us first. TLVs. So we've got the ones we looked at previously, including our passive interface. Prefix /28, our system address /32, and our authentication TLV. But I'm not seeing that BFD TLV. C-type 148. Let's do some debugs. Show log D66. Debug router ISIS. And it's going to be in our hello packet, if I'm not mistaken. So yeah, so it's in addition to our hello PDU. So we should see it in our hellos. See show log ID 66. Oops, detail. All right, so we finally got one. Oh, nice. So here's our type 148, our BFD enabled TLV. So multi-topology 0, protocol IP version 4. Huh. And this is, so this is sourced from us, headed to N2. So if this is amongst these TLVs, maybe it's going to be, I don't know, maybe it'll show up in N1 on N2 within the N2 link state database. So show router ISIS database level 2. Let's take a look at N1s. Because again, the source is router 1, and we see that type 148 TLV being transferred. So it's just not showing up. Or maybe it's not supposed to. Because I'm just curious, like what? So multi-topology and protocol. So that's our multi-topology. That's our protocol. But what else is in there? That's what I'm curious about. What can we do? Wireshark. Let's try Wireshark. Okay, well, well, before we get to the TLVs, let's just look at BFD. So yeah, so we've enabled BFD on top of ISIS, and you can sort of judge by the time here. You can see how frequently that router N1, which has the interface 10.1.2.1, is sending these control messages, as well as how frequently that router N2 with the address 10.1.2.2 is responding to them. So I mean, very, very, very frequently. Stop it right there. Let's see. So we've got BFD. So you see how it's, I'm sorry, hold on one second. All right, I'm back. So we could see just how frequently that BFD sends and receives its control messages. So that allows it to, just going back to our PowerPoint presentation here, that allows it to detect these link failures and tear down that adjacency. Each time it doesn't receive a certain number of these packets, that's going to trigger uh, bidirectional forwarding detection to tear down this adjacency, thus generating that link state update or that change in the link state, uh, forcing the particular router to generate a link state update and flood that update to its neighbors. But what I'm looking for is I'm looking for a hello. Oh, there's one. I thought there was one. Okay, a hello. So I want to look at that type 148 TLV. Here's our type 148 lin3. This is our BFD enabled TLV. However, it's specifying unknown code. Type 148 lin3. Type 148 lin3. I mean, this is TLV, but it's saying unknown code. Code not implemented. Contact Wireshark developers if you want to support it. Okay. So I guess I just have to contact the guys at Wireshark and ask them to add support for the ISIS BFD enabled TLV type 148 lin3. I'll do that later. I won't I won't drag this on any longer than it's already going on. But let's go back to our presentation. So I believe that's it for this particular module. Let me go ahead and /add and save that. So let's just go back over our goals. Debugging, observe router adjacencies forming via debug. We did that. Let's just, all right, observe link state protocol data units via debug. All right, that's what that's what we're doing right now. So let's see, observe ISIS JSON form debug. Let's do that now. No debug. We're going to shut down ISIS, configure router ISIS shutdown. And we're going to debug router ISIS adjacency packets across our interface to N2. And then bring ISIS back up. Let's take a look at our event handler. All right. So here we have our adjacency forming via debug. So we've accomplished that goal. Let's see, routing policy, allow direct or local routes to be redistributed into ISIS. Let's take a look at that. Configure router policy options. And we did that within our entry 1. We specified from protocol direct to protocol ISIS in the action of accept. Apply to ISIS as an export policy. We named our policy export direct routes. Let's jump into the ISIS configuration. And as you can see, we do have that policy applied as an export policy. Configure the global router ID on each SR. We did that via the configure router ID command. Configure all service routers with an area ID of 0. We did that. Oh, I'm sorry, an area ID of 49.00. Also level 2 only. We did that. Configure each router interface as a point-to-point circuit. We did that. Configure a wide metric of 5,000 on each router interface. We did that, as well as specified wide metrics only on level 2 intermediate systems. Configure MD5 authentication using the key myISIS key. We did that. We specified the authentication type MD5. And this is our my-ISIS-key in plain text hashed. Enable IPv4 BFD. We did that, as well as looked at the RFC for it, as well as dissected the TLV. Unfortunately, Wireshark doesn't support the type 148 Lin 3 TLV. So we couldn't go too deep into it, but we did see it in the 7750. Let's see, where is that at? Here we go. So we at least got the MTID and our NLPID on the 7750. I don't think we even got that in Wireshark, did we? Nope. So the point being that the goal was accomplished. Configure BFD on all router interfaces participating in ISIS. Let's just take interface 2 and 2. We did that. Configure BFD with a transmit interval of 100, a receive interval of 100, and a multiplier of 3. We did that. Our transmit interval 100, receive 100 multiplier 3. And alter BFD's default parameters to force the SFM or CPM to manage the sessions. Now, we can't virtualize this, but like we touched on earlier, in the nature of keeping our data plane and our control plane completely separate, we would want the CPM to process those BFD control messages as opposed to the IOM to process them. The IOM processes them by default. And if we were in a router or a service router that supported this type of segregation between data and control plane, that would appear under the BFD configuration. So it would appear right here. You would have the option underneath echo to specify type. And by specifying type CPM NP, which again isn't here, but if this router did support it, the option would be right here. So that's where you would enter it. And let's just take a look at, let's do show router BFD session. And we can see that the type is IOM. So by default, our input output modules are processing all of these BFD messages, 3587. So in just that short amount of time, we've sent another 200 messages and received another 200. So if, again, this router were capable of instructing the CPM to handle those BFD messages rather than the IOM, which it does by default, that option would be right here. And if we specified CPM, type CPM NP, then the next time we ran that sessions command, we would see the type as CPM NP. So I believe that's it. Let me go ahead and save all the configuration. So we've walked through, at this point, we've walked through bringing the SR from an initial out-of-the-box configuration. We configured its hardware, its input-output modules, its media-dependent adapters, as well as its network and access ports. We've configured its system name. We've configured the router ID. We've configured logical router interfaces, and we've bound physical ports to those logical router interfaces. We've also gone over debugging and examining protocol data units. We've gone over creating routing policies and applying those policies to protocols as export policies. And we've gone over configuring bidirectional forwarding detection as a mechanism to detect link failure on top of our dynamic routing protocol, or our link state protocol, or interior gateway protocol, which in our case was intermediate system to intermediate system. So the next video is going to get into the label distribution protocol, and the point of, well, we'll get into that during the video. But yeah, the next video will get into the label distribution protocol. And once we cover LDP, then we'll be able to make the dive into services architecture and actually deploying services on these 7750 SRs. So thank you again for hanging in there with me. I know this was a few hours, but I mean, it's things take time to cover. So as always, please, if there's anything I could have improved upon, any misinformation, let me know. I will correct them. And you guys have a good one. I'll see you later.